In this video, we are going to talk about Riemann sums. So the Riemann sum is going to help us compute the exact area under curves. Let's say, for example, we are given this curve here, y equals f of x, and we want to compute the area that I'm shading here from a to b, that's the interval ab, and we want to get this area, the exact area. Obviously, there is no geometric formula that's going to help us do that. But by using the Riemann sum, we would be able to find a formula, an expression that helps us get this exact area. So what we do is we subdivide, for example, AB, the interval AB, into subintervals. So we have tiny intervals. I'm going to label this C1. I'm going to label this C2. So we keep going. And at a certain point here, I don't know how many intervals we have. You can have 5, you can have 10, you can have 1,000, you can have 1,000,000 intervals. So here I'm not going to limit myself and say I have 10 subintervals. Let's say just I have n intervals. So I'm going to label this Ci. So we have n subintervals. So that means n tiny intervals of, let's say, equal width. So the width here is the same. So that means this distance here from A to C1, I'm going to label it delta x. So I'm going to label the width delta x. So from C1 to C2, we're going to have delta x, and so on and so forth. Now, what's an expression then of delta x? I'm going to write it to the right. So the width here, delta x, remember it's not delta times x, it's just a notation. Delta x is equal to b minus a over n. And n here is the number of rectangles that you want, or the number of subintervals. So from A to C1, we're just going to draw a rectangle. And let's say here we were using right endpoints. You will understand what I mean by right endpoint. So that means from the interval, on this interval A to C1, I'm going to use the right endpoint of that interval, which is C1. So that's why I have a vertical line at C1. I go up until I hit the curve and I go across. And that gives me my first rectangle. And from C1 to C2, the right endpoint of that subinterval is C2. So I'm going to draw a vertical line on C2 until I hit the curve, and then I go across. And then I'm going to keep doing that at C3. If I had C3, I go up. And then C4, at Ci, I will have something like this, and so on and so forth. So now the goal that we have here is we're going to approximate that interval, that area, with the area of these rectangles. So we're going to compute the area of each rectangle and add them all up. This will give us an approximation of the area that we wanted to compute. But remember, we want to be able to find the exact area. So that means the more rectangle we have, the better the approximation. And if we want to have an exact area, then we should have infinitely many subintervals. And when you understand it, when you hear infinitely many subintervals, now you imagine that we're going to compute the limit as n approaches infinity at the end of the day. Okay, so that's the plan. Now, before we move on, we have those endpoints C1, C2, Ci. We need to find an expression for them. So C1, for example, C1 is equal to A this number here, A, and then plus this length. And we know what that length is. That length is delta x. Because remember, over each subinterval, we are picking the right endpoint. And we can do the same analysis for the left endpoint, but I'm just going to focus on the right endpoint here. For the left endpoint, the analysis is exactly the same. So now, if we want to compute C2, C2 would be equal to what? This is C2. C2 would be equal to C1 plus delta x. So C1 plus delta x, which is equal to what? We know what C1 is. C1, which I'm going to write here in yellow, is equal to A plus delta x. If you look up here, that's what we have. So A plus delta x, and then plus another delta x. So at the end of the day, C2 is equal to A plus 2 delta x. So look closely. C1 is equal to A plus delta x. C2 is equal to A plus 2 delta x. And you can already see a pattern. If we continue, you will see that C3 is equal to A plus 3 delta x. And more generally, what is Ci? And this is what we're going to retain. Ci would be equal to A plus I times delta x. Remember, I is a positive integer. So that's the formula we're going to retain here. But also, when we picked Ci, for example, when we had C1 here on top, we drew a vertical line until we hit the curve y equals f of x, for example. So that's what we had for C1. So this point is f of C1. So for each point, C1, C2, up to Ci or Cn, we computed f of C1, f of C2, f of Ci, and f of Cn. So we're going to compute f of Ci. So we computed, let me just write it here, f of Ci. So we have Ci, and f of Ci gives us the length. F of Ci gives us the length of the rectangle. So we have the width of the rectangle, which is delta x, and we have the length, which is f of Ci. So if we want to compute the area of the rectangle would be equal to f of Ci times delta x. Now, what we're doing is we're going to add the area of this rectangle, all the areas. And now that we have learned the sigma notation, the approximation of that area, so the approximation of the area is equal to f of Ci times delta x, and then we add them all up. So we have the summation here from I equals 1. Remember, we are using left and right endpoints up to n. So this is an approximation of that area. And remember, n is the number of rectangles. But we wanted an exact area. But before we go further, this summation here on the right hand side, this is what's called the Riemann sum. And if we want the exact area, so the exact area, we need to have as many subintervals as possible. So it's going to be equal to a limit as n approaches infinity of sigma from I equals 1 to n f of ci delta x. So this is the formula for the exact area. And remember here that ci is the right endpoint, so it's equal to a plus I delta x. And we even know what delta x is. So it's equal to a plus I, and what's delta x? We saw that delta x is b minus a over n. So that's the formula for ci. And we then have an expression for the exact area. Remember, we can do this same analysis for the left endpoint and for any point in that subinterval in general. But what I want you to understand at this point is to be able to find the formula of the exact area using right endpoints, as we just did in this video.